So thank you, Sean, very much for the introduction, and thank you for everybody for turning up for this seminar. It's a great pleasure to be with this very international group of theorists, mainly theorists and modelists in the area of glass. I shall therefore restrict myself to suggesting that experimental findings might continue to throw up things that would be of interest for the point of view of theory and modeling. My overall theme is, how do you extend the energy range of the glassy state? Now, as Sean has already hinted, this audience in particular doesn't really need any introduction to glasses. I will say I take a rather strict view of what is a glass, that it's not any old amorphous solid, but it is something that has come from the liquid. You could, of course, cool the liquid faster and go through the transition into the glassy state sooner at higher temperature, or you could cool more slowly. You would thereby get a range of states. You could equally well have an as-cast glass and at ambient temperature try to change its state, its energy. Now, of course, you could do that by some annealing treatment well below TG. You could certainly raise its energy by irradiation. The focus for this talk will be something that would be rather unusual in the broader world of glasses, and that is using mechanical plastic deformation as the way of changing the structure. Now, it's worth thinking that in the world of conventional metallurgy with polycrystalline metals, mechanical deformation is not only used to change shape, but actually used to change properties, and in particular to optimize properties, to harden a metal. So the query is whether there's a similar range of things you could do with metallic glasses. And one thing we can immediately say is that unlike some other categories of glasses, they do show considerable plasticity, certainly in compression. Here's an example. You see a 0.5 millimeter scale. I should also just remind you that once upon a time, people felt that metallic alloys would be very difficult to get into the glassy state. The liquid would have to be cooled very fast by some extreme process, such as that's shown on the screen right now. But it's now understood, has been understood for decades, that if you adjust the composition right, you can have glass formation at really rather low cooling rates of the liquid, and you can therefore cast fully glassy in bulk. Here's a little section of a cylinder, the diameter of a dime. This is a little composition map showing that there are rather specific compositions where the glass forming ability is higher, and that is quantified as the diameter of the cylinder that you could cast and still have it be fully glassy with no crystalline content. And here it just goes up beyond a centimeter at best. I would highlight, however, that those special compositions with high glass forming ability really are quite tightly defined. And I would rather provocatively suggest that you might even think of these bulk glass forming compositions as something like rather special intermetallic compounds, which happen to have an amorphous structure, not a crystalline structure. But for sure, the structure is ordered. As you can see by looking at the thermodynamics, you just make your calorimetric measurements and plot the delta G curve for the glasses relative to the underlying polyphase crystalline state. And taking the derivative, of course, you get the entropy difference, which is essentially zero down at the temperatures where you're forming the glass from the liquid. So these are highly ordered systems, but clearly not crystalline. And in the best glass forming compositions, palladium based, for example, you can get fully glassy cylinders several centimeters in diameter. The main commercial application for metallic glasses, which is genuinely quite an important one and becoming increasingly important, is as a soft magnetic material for transformer cores and multiple magnetic devices. That's an established area which will, I think, make more progress. Scientific interest in more recent years has been, given that the glasses can be made in bulk, maybe one should be looking at structural applications and their mechanical properties. I won't dwell on that except to say that there are genuine reasons for interest. So this is a map of just the properties of engineering materials, metallic engineering materials. And the dark ellipses are the elastic limit, the strength, in essence, of various metallic glasses as a function of density. The point is they come at the top of the distribution. So these are the hardest metallic alloy materials known, basically. Now, if you were a really conventional metallurgist, you might work on steels, and you could have a steel of a particular yield strength on this log-log plot. You could anneal the steel, you would reduce its strength, which might seem to be a bad thing to do, but the steel would automatically get much, much tougher. It would be much more resistant to cracking. So in these conventional materials, you always have this trade-off. Do you want a high flow stress of the material, or do you want a great resistance to cracking? And by and large, you cannot have both. And steels are the classic example of that trade-off. Well, you could then pose the question, what's the material that would give you the highest product of these two things, flow stress and the toughness? And that product you could call damage tolerance. That's a terminology promoted by Rob Ritchie in Berkeley. And that would put you, of course, towards the top right of this diagram. And it's simply astounding that of the materials known, the one which has the highest known combination of these two parameters is a metallic glass. I think that's astounding because the standard thinking about toughness is that you need to do something to block crack propagation, and that means having a microstructure. You have second phases in there or some type of patterning in the material. And almost by definition, we would think of the glass as having no such microstructural pattern. So it has this great combination. It also has high absolute values of toughness. Coming to the energy of the glassy state, you of course have the crystal, you have the liquid, then the supercooled liquid. My point is simply that the liquid line and the crystalline line are not parallel. So you have a heat of fusion at some temperature, and you might have thought that when the glass crystallizes at a lower temperature that you'd have the same heat of crystallization, but you don't. It's only about 40% typically of the heat that you would have had at the liquidus temperature for the alloy system. And of course, the difference is that in between you have some sort of excess specific heat of the supercooled liquid, which of course is telling you exactly that there is ordering as you cool it towards the point where it enters the glassy state. You, of course, depending on your cooling rate, would have different energies of that glassy state. And here I've just given a little calibration of cooling rates over some 23 orders of magnitude or something, so more actually. But anyway, we'll say a bit more about those later. Here is an energy scale looking at the energy of metallic glasses relative to the crystal. So I've already said the relaxed glass is about 40% of the standard heat of melting above the energy of the crystal. Of course, your as-made glass is not relaxed. If it's been melt spun with an extreme process, cooling at 1,000,000 degrees a second or something, it most certainly has a higher energy than the relaxed system. But even a bulk glass has an energy that's a bit higher. And each of these energies can be in some way related to the cooling rate that you would have to use if you wished to make a glass of that energy by cooling the liquid. My interest in this talk is principally about if you do have a glass, what can you then do to it to change its energy? And in particular, I'm going to be interested in what you can do to increase its energy. And there's a reason for that. It's well known, especially for the glasses of importance for their magnetic properties, that if you anneal them, which is quite a good thing to do to improve their soft magnetic properties, they do become horribly brittle and difficult to work with. Of course, you don't want them to show that embrittlement. You'd like them to show something in exactly the opposite direction, becoming more difficult to crack. And that would mean increasing the energy of the system, so doing something that's opposite to annealing. And we compare here various mechanisms of injecting energy in the system, which I won't dwell on for the moment, except to say that one of those mechanisms would be irradiation, which takes you off scale on this diagram potentially, but it is not practical in most cases, so we won't look at it anymore. Why would you want to expand the energy range? Well, I've already given some reason for that. I'll contrast relaxation, lowering the energy of the glassy state, potentially down to ultrastable states. Prospect of greater resistance to crystallization, you'd certainly have higher hardness and creep resistance, and we'll say a little bit more later about the glass transition behavior of ultrastable states. Going in the opposite direction, if you thought of relaxation as aging, then its opposite you might regard as rejuvenation, which is a name often used, derived from the polymer community. You could go towards highly unstable states, and they actually have their own interest because they could be capable of very fast crystallization, which is of interest if you're looking at computer memory and switching, for example. And we would certainly expect them to have better plastic flow behavior, which would be generally favorable for mechanical uses. And you might even have the long imagined impossible property of metallic glass, namely tensile ductility. And I'll say quite a bit more about that. But more or less from the earliest days of mechanical property studies on metallic glasses, it has seemed impossible to have true ductility. That is to say, the capability for the sample to remain of stable geometry while plastically deforming in tension. This map of the mechanical properties, mechanical behavior of metallic glasses is due to Franz Spapen and must be one of the most cited diagrams and papers in the metallic glass field. He highlights how the behavior is different as a function of temperature and as a function of applied stress. And basically at bottom right, high temperature, low stress, you get straightforward viscous flow of the glass, liquid-like flow, if you like, and it's undoubtedly homogeneous. Top left, you're dealing with room temperature behavior, high stresses at the yield stress of the solid, and that's where you find the inconvenient truth that the flow in this case, unlike a polycrystalline metal, is not homogeneous, but shows this very sharp concentration of the shear flow into very thin shear bands. And that's generally associated with the phenomenon shown top right, that for a metallic glass put under increasing load and getting increasing strain, you go into a yielding behavior, you go from elastic to plastic, but as soon as you enter the plastic regime, and again, unlike a polycrystalline metal, you soften rather than harden. And that's what gives you the instability, of course. So it's this softening introduces the possibility on a strain rate plot of having coexistent high and low strain rates at the same shear stress, which of course means you can have high shear rate in the band and negligible shear rate outside. These shear bands are certainly very interesting. So this is a metallic glass wire, bent, you can see the band patterns. At first sight, you might think those are cracks, but they're absolutely not cracks. If you look at the surface up close, you can see it's a perfectly nice, clean material, no penetration of a crack at this point, very clear shear. But it's a very remarkable phenomenon. So this wire was bent, you then let go, you get a certain amount of elastic spring back, and you kind of regions where you've got neighboring shear bands which are very close to each other. The shear bands themselves are momentarily liquid-like in their flow behavior. And so when you let the wire go and this surface goes into some compression, you might just have a little sliver of solid trapped between two liquid-like layers that pops out under the compressive stress when you let go of the wire. However, intriguing as all of that is, by and large, shear bands are regarded as seriously bad news, because if you have a bulk sample in plain tension, you just get early catastrophic failure, essentially without any noticeable plastic flow, because there is plastic flow, but it's localized in this single plane. So the stress strain curve is profoundly uninteresting, if you like. What's the great hope? Well, the great hope is that if you rejuvenated the glass enough, you would eliminate this shear banding behavior. So if you took it in terms of this plot, what we saw before was a variation of stress with strain rate like this, the idea of having two values coexisting for the strain rate. But if you rejuvenated the material and somehow softened it, and you would undoubtedly have an earlier entry into plastic behavior, you could imagine a plastic behavior like this and a system that would actually show strain hardening rather than strain softening. And that, I'm going to suggest, has always been a sort of holy grail of the experimental metallic glass community. And what I want to look at a bit is how far have we got towards grasping the grail. Let me first say, you can do plastic work on metallic glasses, and you can measure the effect in terms of stored energy. This is how it looks for some cold rolling of a metallic glass, really ancient work early in the field, 1976. And it shows you do mechanical work on the system, and somewhere between 1 and 10% of that mechanical work is stored as some sort of defects in the system. Very interestingly, that's just the same number as you'd get for a polycrystalline metal, where if you mechanically work it, most of the work you exert is dissipated as heat, but somewhere between 1 and 10% of it typically is stored as extra energy in the form of increased dislocation density, etc. So this starts to look a little bit similar to crystalline systems. You might be surprised to know that metallic glasses can be extremely heavily deformed. So just to give you some headline figures, this is the idea of rolling a sheet between two rollers. You can roll to 92% reduction in thickness. So your final thickness is only 8% of what you started with. Or you can draw metallic glass wires, so your final cross-sectional area is only 7% of what you started with. So these things are capable of being very heavily deformed. Something that has been a fashionable process recently is this so-called high-pressure torsion, where you put a thing shaped roughly like a coin in the middle. You twist the things above and below in contrary directions, and you get enormous strains. This is not a strain of 925%. This is a strain of 925. So you can do as much as you want there. Now, with that high-pressure torsion technique, unsurprisingly, you can measure increased energy of your system. And this is, I think, the world record value for this technique. And it's storing about 24% of the heat of melting as a result of that deformation. So it's quite a substantial change in the energy of the system. Now I'm going to take you to an utterly, utterly different world. We're sitting with a bulk metallic glass sample. You have to have a mind's eye picture of just a little cylinder of this, and you're going to load the cylinder along its axis in compression. So it's essentially static loading. You're below the yield stress, so there's no plastic flow. You load at room temperature, so there are no temperature effects, but you load for a long time, well, a day. And you come back and you measure the energy of the system, which you can do calorimetrically. So the as-cast glass would have some energy. It's the area here. We'll see a bit more about that later, but it's something just to compare to. Evidently, after this elastostatic loading, you've stored a lot more energy down to the green line. And if you were to do the loading not at room temperature, but at liquid nitrogen temperature, you would store even more energy. So it's obviously not to do with the amount of flow, because actually, insofar as you do have flow at all, you obviously have less flow at liquid nitrogen temperature than you do at room temperature, less creep. So you have an energy storage mechanism, apparently within the elastic regime. There's a tiny amount of creep of these samples. There is a tiny strain. Let's look at that business of how you might accumulate energy in a system. So we imagine you might have some starting state of your glass, which we're measuring here in terms of its enthalpy, and it's going to go to some final state as a result of your processing. Well, clearly, if you start with a higher energy and you then process it, it's more likely that your energy is going to go down. And if you start with a lower energy, it's more likely that it's going to go up. But where will it end up? Well, that depends on a balance between, in some ways, something that we might think of as the injection of energy, defects you're putting in through your processing. And I'm deliberately being very general here. This processing could be a radiation, it could be plastic flow, it could be this elastic loading. The more intense your processing is, obviously, the more likely your energy is to rise. But fighting against that is always a natural relaxation, a sort of repair process that would reduce your defect density. And clearly that's favored by higher temperature. So if you were at lower temperature, liquid nitrogen, that would, of course, help you to accumulate damage. So going higher up in energy is both a matter of more intense processing and of sitting at lower temperature. The other thing I would mention is, of course, you could accelerate accelerate that relaxation not only by raising the temperature, but as it turns out, by lowering the pressure. So hydrostatic tension in metallic glasses is known to accelerate all the atomic mobilities. We'll see more about that later. Anyway, here we are on this plot, and we are accumulating some energy with this very strange business of loading in the elastic regime. Life is about to get even stranger. You will recall, in relation to stored energy from plastic work, I said, well, you do some work on the system and you store some small fraction of that as stored energy. And that fraction might be between 1 and 10%. Well, in this elastic loading case, it's not totally elastic. There's a tiny creep strain. It's rather easy, you know the stress very straightforwardly, you know that creep strain, to work out the mechanical work done on your sample. It's also quite straightforward calorimetrically to measure the new stored energy as a result of that. You take the ratio, and what you find is that you're storing far more energy than you exerted through work done. So you must have induced some endothermic disordering process that's drawing heat in from the surroundings. That can be the only source of this extra stored energy. So it's an interesting little process that might deserve some further study. Now I'm going to take you to yet another totally different world. And this is a world that I got into in the way that academics do because they don't necessarily want to, but they're forced into it. So I had to teach an undergraduate class in nuclear materials, so materials for nuclear energy. And it got me into this strange phenomenon of uranium. This is uranium metal. And you'd have a fuel rod in your reactor, and any reactor is under active control, so the temperature fluctuates. And they discovered quite early on that under temperature fluctuation, uranium fuel rods get longer and thinner. Their volume does not change, but their shape changes. This is the actual cycling. This would not happen if uranium was a cubic metal, where thermal expansion is isotropic. Uranium is in fact orthorhombic, and it's dramatically anisotropic in its thermal expansion. Indeed, one of the lattice parameters over a large temperature range actually contracts as you increase the temperature. Anyway, the volume overall goes up, of course, but anyway, the point is that uranium sort of tears itself apart as neighboring grains wish to change their shape in different ways. That's not really how you would ever expect that a metallic glass would behave. You don't have grains, but for sure you don't have a single crystal structure either. So you, at a local enough level, you could imagine you have anisotropy in a metallic glass, and therefore you could have some very vaguely similar effect of competing local anisotropies. And you could test that by thermal cycling of the metallic glass. So this just takes us from a temperature around room temperature down to essentially liquid nitrogen temperature. And with everything in the glassy world, one is tempted to scale it relative to the glass transition temperature, which is what I've done here, which is why the room temperature looks like a range of temperatures. It's a range relative to the TG of different metallic glasses and a somewhat different temperature range at the upper end. Key point, though, is for metallic glasses, if you get any thermally induced relaxation, typically by annealing, and people would talk about alpha relaxation around the glass transition and beta relaxation, these will be characteristically found above 0.6 of TG. This is essentially all happening below 0.6 of TG. So this is not your standard thermal annealing behavior. And it's been done for a variety of glasses in different geometries. What's astounding is that this has an effect. You might have thought it would have no effect on the glass, but actually you induce extra stored energy. And it seems to be specifically to do with cycling the temperature, because you don't get a large effect, possibly not zero, but you certainly don't get a large effect by just holding for a long time in liquid nitrogen. And that work has now been looked at by multiple groups across the world. They verify the stored energy. They get moderately similar values in a vast range of different compositions. The extra stored energy is comparable with that elastic loading that I talked about, and is about half of what you might get with simple cold rolling. But it is amazing that for something that is obviously within a low strain regime, that you have any effect at all. Of more interest to the mechanically minded people is that it's pretty much universal that when you do this cycling, the mechanical properties improve. You get greater and greater plasticity. If you relax a metallic glass, you would reduce the plasticity. In this case, you can partially relax and then cycle it, and you restore greater plasticity. So it's almost, if you think of embrittlement of the glass by annealing as seriously bad news, this cycling afterwards allows you to bring it back from the dead. So probably this idea of the Romans throwing themselves into cold baths and hot baths was not such a bad idea for rejuvenation. If you fully relax the glass, it seems to be irrecoverable. Presumably it becomes so homogeneous that when you then cycle it, you don't have different regions acting against each other to give a rejuvenation effect. Just quickly to say, this is shown in one diagram here, but it pops up again and again and again with different glasses, different groups. Whoever measures it sees the same effect of greater strain after the cycling. Yet another group. Of course, those strains might not be of great interest. People interested in metal systems that might have problems with cracking are, of course, interested in the toughness. We mentioned that earlier. The toughness is roughly doubled as a result of the cycling process. And there's other work that shows even bigger effects. So that's that story. That is staying with very tiny strains, well within what you could consider to be an elastic regime. I now want to take you to yet another world where we're going to go back to plastic processing, but we're going to learn something from what I just said, that if you could manage plastic processing for very, very low strains, very low plastic strain, and under high hydrostatic constraint, you might achieve some interesting results. And remember that the hydrostatic business was important for whether you got relaxation or not. Well, there's this work from some time ago, Chris Hsu at MIT is involved, where they looked at a metallic glass in a very particular test geometry, which is a simple enough one. It's a cylinder with a machined notch. You then put the cylinder into tension, and you compare the material that deforms in the region of the notch, plastically deformed, with what would happen without any notch. Well, without the notch, you'd get a rather low yield stress for the system, the material flows, and the strain could be large. In this case, you build up lateral tension as well around the notch, so you get a triaxial stress state with the shear components being rather low relative to the hydrostatic. So you get less plastic flow, but a much higher hydrostatic tension than you get here. So in terms of generating damage, that's rather slow here. You don't have much plastic flow. In terms of repairing damage, that's rather accelerated here because you have lots of hydrostatic tension. So much so that the net effect is that the repair of damage seems to win over the generation of damage. So you actually end up with a metallic glass in the notch region that's not softer, but harder. It behaves as though it has been annealed. And you can measure that in the stored energy. So this is a case where the sample is more relaxed after plastic deformation. So the opposite of the normal effect. It gives us, however, some sense of the importance of that hydrostatic component. So that's what we pick up next. And this is where I jump into the picture with my obsession with rejuvenation rather than relaxation. So we now invert the Chris Hsu experiment. We keep our notch cylinder, but we put it in compression rather than tension. So now you have your, this gives you a sense of the original height in the notched region. It's been compressed, you get plastic flow. We interpret that plastic flow to be entirely without shear banding because you just don't have the capability of producing surface steps that would allow you to accommodate shear banding. The macroscopic load to get this flow to happen is much higher. You can get higher stresses. When you measure this is a cross section of the notch cylinder, you measure the hardness. As expected, the hardness goes down. So this is a system that has been rejuvenated. It goes down a lot, by as much as 36% reduction in the hardness. What we did not expect, which was perhaps rather stupid, was how much of the material would be rejuvenated. We expected a sort of coin-shaped volume here in the notch region, but no, it extends up and down considerably. The total dimension here is 4 millimeters across. So you've got a little, and remember this is a cylinder, so roughly speaking, this blue-green zone is its own little cylinder of reduced hardness. And it follows a different hardness trajectory as a function of what appears to be the plastic strain. And that's presumably something to do with the hydrostatic stress effect. It's getting very much softer and in fact comparable to the material in shear bands in the otherwise deformed metallic glass. Now, what we can do further is measure the energy of this. So we take the notch material out. You can cut a little bit out of the rim, notch edge. You do your DSC traces. You measure the stored energy. It's enormous. It's over 40% of the heat of fusion as extra stored energy in this system. If you translated that, as is rather easy to do, to an effective cooling rate that you would need to use in order to achieve that same energy by direct quenching, the quench rate you would need would be about 10 to the 10 Kelvin per second. The actual quench rate of the original bulk glass was 10 to the 2, and indeed could never be 10 to the 10. You could never make the cross-section small enough, of course. So it's saying that this mechanically treated sample has an energy that is characteristic of a cooling rate that is 7 to 8 orders of magnitude higher than the actual cooling rate. Now, do not misunderstand me. I am not saying that this is the same structure as a material that would be obtained by cooling the glass at 10 to the 10 Kelvin per second. Certainly it will not be, but it does have the same energy. So there's something interesting to compare there. And this just shows you where that energy would sit on this scale of things that we saw so far. Now, if you remember that central zone, this is a little cylinder. So next step in the work is to say, well, actually, that's quite big enough that we could do our processing that we did before. We could then cut that little central cylinder out and treat that now as our metallic glass that we do our experiments on. And the simplest experiment to do on it would be a compression. And the result is rather astounding from the point of view of metallic glass world, because this could equally well be stress strain curves for a polycrystal. You go up elastically, you could unload, you come down elastically, but if you start to go into yield, your flow stress increases, you unload, and then when you reload, your flow resumes, but at the increased onset stress, which of course is classic strain hardening. And you can get quite a significant amount of this hardening behavior. The onset of the flow is undoubtedly earlier, so the material is softened in this rejuvenated state. But once it does flow, the flow is beautifully uniform, not like this jagged shear band mediated flow that you get in the as-cast glass. So it's quite different behavior. That's in compression. And it suggests that we can go beyond what Evan Ma had suggested was a pretty fundamental problem with metallic glasses, that they just lack any sustainable capability to stabilize themselves against tensile flow, where you have a fluctuation in strain or strain rate, which I've mentioned earlier. So what about shear bands? If you really are getting strain hardening, you should have removed the motivation to get shear bands. Well, if you have the as-cast glass and you put it in compression, you immediately see shear bands, and they're entirely evident. This is the equivalent surface of the treated sample, going to increasing compressive strain. And at least up to this value, about 3% strain, you're getting plastic deformation for sure, but no shear banding. Later on, shear banding does kick in, but you're still getting overall much better mechanical performance. You can do electron microscopy of the material. You can look at the shifts of this first peak. I should say you could imagine, of course, doing this type of experiment in a synchrotron, say, to measure with great precision. It fails miserably in this particular case being applied to these metallic glasses. And the reason is we're interested in small shifts in this that might reflect structural change. But of course, you also get shifts in this from any elastic strain. And in a metallic glass system, you can have elastic strains up to 2% that completely swamp the structural component. But doing it in a TEM thin foil, you remove that problem. And you can see that in the rejuvenated material, you have greater interatomic distance. So your first peak in S of Q, of course, moves to lower Q values. So going from as cast to rejuvenated, you shift to the left. So what then has happened? Well, basically, if you looked at the hardness of your as cast system, you mechanically treat it, you soften it. When you then deform it, of course, it tries to go back to its original hardness. So this is your strain hardening. It doesn't last for long, but it's a perfectly real effect. Similarly with the energy, by rejuvenating the system, you pump energy in. Now, when it strain hardens, you go back to a lower energy. So this is rather nice because this is real strain hardening, but it's absolutely the opposite of conventional Taylor hardening in polycrystals, in the sense that conventional hardening is to do with increased defect density, more dislocations. So conventional hardening is always associated with an increase in energy. This is associated with a decrease of energy. It's back to front in that sense. Structurally, you rejuvenate, you move your S of Q to lower Q values by the mechanical treatment. As soon as you start to deform your rejuvenated material, it starts to recover and your S of Q starts to move backwards. So is actually actively relaxing, going to lower energy states as you deform it. You can do it, just I should mention, in tension as well, and you see shear, you see the strain hardening in just the same way, although the experiments are very much more difficult to do. Quick note on the strain hardening. This is a true stress, true strain plot for a very conventional polycrystalline stainless steel. So you get a clear elastic regime, clear onset of plasticity. You can measure the rate of hardening. And you could normalize that relative to the yield stress if you wanted. This is the equivalent for our metallic glass. You can hardly tell that there is a break in slope here, but it's just, there is really. And quite a clear distinction, as we saw. If you look up close, there's in fact quite a clear distinction between where you're elastic and where you're plastic. In any case, your initial hardening rate is very high. And we can look a bit further at that. Why might that be? Well, a very, very crude idea would be that if you're getting strain hardening in a crystal, actually very few atoms in the entire system contribute to that hardening. It's only going to be where you've got specific dislocation configurations. On the other hand, in the glass, perhaps more or less every atom can do its little bit to help the system settle into a lower energy, harder state. There's no doubt that the contrast is enormous. So this is hardening rate as a function of strain. So initially it's very high and it decays. Our stainless steel that we just saw earlier is lurking somewhere in here, and that's this blue line down here. So very low hardening rate that, however, stays rather steady with increasing strain. You can take a rather exotic crystalline material, ultra fine grained dual phase steel, that shows much higher hardening rates, but again maintained for quite high strains. But by far the most rapid decay of the hardening is the metallic glass in tension. So it has a wonderfully high initial hardening rate, which is probably good news, but it doesn't last for long. It decays very fast, and that's going to be bad news from a mechanical properties point of view, because there's a well-known in conventional metallurgy construction due to Considère, who says, well, you should look at the hardening rate of a material and compare it with the absolute flow stress. They, of course, are the same units and strain is dimensionless. I've normalized it here. When the two are the same, this is the curve of hardening rate and the curve of hardness, if you like, or flow stress. And where they intersect, that's where you transit from the material being unstable against necking in tension to being stable against it, to being unstable. So your onset of necking happens beyond that intersection point. And for annealed copper, nice soft crystalline metal, that intersection point is at really high strains. So copper is very ductile. Even our exotic ultra-fine grained steel is moderately ductile. The metallic glass, however, the intersection point is here because that hardening rate decays so extremely rapidly. So the bad news is, I think, that although we've reached this sort of holy grail of achieving strain hardening in a metallic glass, it's brought us some tensile ductility, but not much. And we could sum this up in various ways, but I'll just say it's really a totally new mechanism of strain hardening, quite different from anything to do with dislocations, and the energy goes in the opposite direction. But in the end, it hasn't, in fact, brought us very much improvement in ductility. For the closing little bit of the talk, I want to take you to yet another area. Probably I don't really need to introduce fictive temperature, but basically you could have a glassy state that you make by quenching. You could anneal it, you go to a lower energy, you then extrapolate where you cross the liquid line, you have your TF, you could go in the other direction. So you could have a lower TF or a higher TF. And you would use the fictive temperature as a way of describing your degree of relaxation or relaxation. So let's look at an actual metallic glass case. Here's a differential scanning calorimeter trace. Low temperature, you have the glass, you heat, you go through the glass transition into the supercooled liquid. You could characterize those each in terms of what is essentially a specific heat, which is the gradient on that earlier enthalpy plot. And so your glass transition on heating, in essence, shows up as a step in specific heat. And that's what we see here. And of course, you could idealize it by putting horizontal lines for your two specific heats. You could then draw a vertical line such that the area under the curve is the same as the area under your idealized step, and that would be your definition of fictive temperature. Right now, if I take that same glass and mechanically deform it, I store lots of energy in it. I now do my nice little fictive temperature construction, and I now find that the fictive temperature is significantly higher than the glass transition temperature. So TF becomes higher than TG, that's your rejuvenated state. I could go in the opposite direction. This is a rather fun example of a gold-based glass developed by Jan Schroers at Yale. We made some an awfully long time ago, up to 10 years ago. So inadvertently, if you like, we did a long-term low-temperature anneal. Quite a strong anneal in terms of its effect, because this glass has got such a low TG that room temperature is a very high fraction of TG. So you do get a significant annealing effect at room temperature. And after 10 years, your fictive temperature is way lower than TG. And one way of thinking about that is describing a very highly relaxed state. And you could quantify that degree of relaxation as the difference between TG and the fictive temperature relative to TG. And it's about 14% in this case. So you've gone down by 14%. That would correspond to an effective cooling rate in this case of some 6 times 10 to the minus 4 Kelvin per second. Now, I know that some of you, Ludovic in particular, are entirely familiar with this field from Madison involving Mark Ediger and co-workers of ultrastable, what I might call ultrastable glasses, which are organic systems. And you deposit onto a cold substrate, you get different energy states, and you go to lower fictive temperatures. And basically the idea is you can reach fictive temperatures so low that you could never practically reach them by cooling the liquid or by long annealing treatments. And you get significant overshoots in the specific heat as you go through the glass transition that would be characteristic of annealing, but you get overshoots of a quite qualitatively different kind as a result of this production method for the ultrastable glass. They're at higher temperature and much broader. What's happening, of course, here is that you're depositing your molecules onto a cold substrate, but the surface mobility is 10 to the 4 to 10 to the 8 times higher than in the bulk. So despite the low temperature, the system can settle into a lower energy state than it would be able to do even from bulk liquid, if you like. And I'll take just a couple of sheer laziness, pick a couple of images from Mark's review here to say, of course, as you go to lower and lower substrate temperatures, you settle into denser, lower energy states. This is your thermodynamic line. Of course, you can overdo it. If you go to low enough temperature, you don't have the kinetics, even with surface mobility, to settle into the thermodynamically favored line, so you curve over. But the most relaxed state you can get probably corresponds to about 80 to 85% of Tg being your substrate temperature for this deposition. So you can get wonderfully relaxed states, but of course they're very thin. They've been made by thin film deposition. So this is not remotely a route to a bulk ultrastable glass. It is, however, a route to very interesting phenomena. And of course, with these organic systems, you have the option of using all sorts of optical probes, and you can detect interface movement. So it would be claimed that the glass transition in these systems really looks a lot more like melting, that you have a distinct front propagating from the surface, just as you would have for liquid into crystal. So it's like this ultra-stable glass is so stable. Actually, it's unable to sort of generate a higher energy version of itself internally. It has to propagate from the surface. Whether you would ever see something like that for the metallic glass case, well, certainly it hasn't been seen up to this point, and of course we don't have the optical probes for it. But it is of interest to think, could you do anything similar with metallic glasses looking at ultra-stable stuff? Well, here's what you get if you do one of those notched cylinders in tension. You do indeed get this overshoot in specific heat. It doesn't shift to higher temperatures, but it does become much, much broader than you'd get on annealing. So basically, here is this metallic glass. This is what you get on long-term annealing, very sharp overshoot, quite distinct from what you get as a result of the mechanical treatment. And we're trying to make some sort of vague parallel between this behavior of the mechanical treatment of the bulk metallic glass and this behavior of the deposition of the organic system. We've reproduced part of it in it becoming broader. We haven't reproduced it in moving totally to higher temperatures. What is, however, interesting is when you look at the actual fictive temperatures. So if you take this naphthol-benzene from Mark Ediger's work, you could do long-term anneals, and your percentage shift here, how much does the fictive temperature go below Tg, on annealing is a few percent. In the deposited material, it's of order 10%. If you just did liquid quenching, of course, Tg and Tf are pretty much the same thing, so your difference is tiny. Going to indomethacin, it's a similar sort of pattern, about 10% move downwards as a result of the vapor deposition method. Something I haven't shown you experimental data for, but there's quite a research interest in, is ancient amber, which of course is annealed at ambient conditions, not for years, but millions of years. And there you get values of order 10% again, in terms of this reduction of fictive temperature. If you take our BMG, it's a zirconium-based system, you can do annealing and you get some reductions. You get quite a large reduction on just long-term annealing. If you do our, it's essentially the loading of that notched cylinder in tension, but oscillating the stress a bit, and adding on a little bit of low temperature anneal, we get about 16% shift of T fictive relative to Tg. So again, I'm not remotely claiming that this is the same structure as you would actually get by some other method, but it is remarkable that you can get to such low energies, especially when you consider that this total treatment might have taken some hours, which if you compared with how long you'd have to anneal, say, or how slow you'd have to cool the liquid to achieve the same state, is a factor of roughly 10 to the 9 difference in time scale. So it appears to be the most tremendous acceleration by some mechanism as a result of that hydrostatic tension. And we've looked at it in terms of the diffraction as well, and the this possibly ultra-stable like metallic glass has remarkable consistency of this S of Q peaks, where otherwise elsewhere out here in the untreated material, they're locally quite variable. That variability has gone away in this central region. So to conclude, I'd just like to say, I think even monolithic, I should say metallic glasses, show a wide range of states, roughly 50% of the heat of fusion. You could, of course, use various ways of changing the states, and that can go all the way from very much in the highly plastically deformed regime to something that you would have to regard as something like an elastic regime. There's a clear reversibility element. There is an element by which you can, for example, embrittle the material and then unembrittle it by an appropriate treatment. Homogeneous flow achieves various things, which can be extreme. This very strange business of elastostatic loading, introducing endothermic disordering, and yet noticeably, I didn't quite mention about this particular approach, but it also improves the plasticity of the metallic glasses. Thermal cycling, we might have expected to have no effect at all, but it does. And we are close with the point that the holy grail of suppressing shear banding might have been reached, but we found that the holy grail wasn't quite as interesting as we might have hoped at the outset. And I shall end there. I'll perhaps keep the slides on screen just for the moment in case we need to turn to them in relation to questions.
Yeah, well, thank you very much for a very interesting talk. And yeah, if anyone has any question, you can just go ahead, or if you want, you can raise your hand or type it in the chat and I can call on you.
I think I have one question.
Mm-hmm.
Hello, Lindsay, how are you?
Very well.
Very nice talk. I'm happy because usually in this Simon seminar, I don't get more than 15%, but today it's the reverse.
Oh, good.
Yeah, something about the extreme rejuvenation property you shown that is very interesting. Do you see usually always that the yield stress of your extremely rejuvenated glass is still better, still larger than steels when you do this process? I mean, does the balance of the improvement in terms of mechanical properties is always in a good direction?
Yeah, so I actually don't have numbers in my head for that. It is clear that if you took a classical polycrystalline metal, which has a certain hardness, let's say, and you anneal it, let's say heavily deformed copper, pure copper, and you anneal it, it'll get much softer. The extent of the change of that yield stress of the copper is far, far larger than the extent of the yield stress for the treatments that we've managed to do with metallic glasses. So the treated metallic glass is still pretty hard. It would be interesting to think about how far you could go in even more extreme rejuvenation. And I suspect that we are pretty close to some sort of limit beyond which the glass would simply not be stable. It would crystallize. And we know for sure that you can induce crystallization without temperature rise. You can induce crystallization by mechanical deformation of the glasses. So I think that's the limit we're up against. But I don't think we've softened them so much that they are now softer than, what would have been the comparable engineering materials.
Okay, thank you very much. Just a quick other one. It seems that the elastic properties are not really affected by this extreme rejuvenation. Is that true, or is just a feeling from the curve?
I suspect that this dramatically depends on the treatment. So if we do our thermal cycling treatment, we know that there's a quite measurable change in some type of mechanical property. And as I mentioned, maybe something like the toughness could even be doubled as a result of that treatment. In contrast, the elastic moduli are hardly touched at all. So for me, it's something like an analogy of dislocations in the crystal, that they will dramatically affect the plastic properties, but not with similar dramatic effect change the elastic properties. So we're putting in some sort of local features that have effect on some properties and not on others. That effect on the elastic properties, however, may well not be the same for the extreme rejuvenation. And that is probably something that we should look at, in fact. And we could look at it not only in terms of change of absolute value, but in terms of induced anisotropy of the elastic properties. And I expect that we might find quite considerable anisotropy because the processing is intrinsically directional.
Thank you very much.
So perhaps something slightly related to that last thing. So you talked a bit about how the change in energy or the change in fictive temperature compares to amounts achieved with annealing. Are the changes in elastic and plastic properties for the same change in energy on a similar scale for annealing, or is there some dramatic difference?
They're quite similar, in fact. They're quite similar. Yeah. Hmm.
So Camille, why don't you go ahead?
I think Vishnu raised.
Oh, okay. Then Vishnu, go ahead. Sorry, I only have the videos on. I should turn.
Yeah. So my question was about the figure that's on screen right now. So you define the glass forming ability as the maximum size of the sample which still retains amorphous character, right?
Well, I don't wish to be critical about that. I'd be happy to define it in various ways, like a critical cooling rate or something. But in practical terms, obviously, if you can make it bigger, it has a better forming ability. Yeah.
Okay. So then, does that mean that if I, for any of these particular compositions, if I tried to make a metallic glass of a size that's larger than the value that's quoted here, it would all crystallize?
No, you would find. In say the geometry that we have there, this is achieved by pouring the liquid into a cold copper mold, and obviously the material in direct contact with the mold, which is the periphery of the cylinder, is cooled rather fast, and the cooling rate decreases steadily towards the central axis. So what you would find is you'd have an annular material that would be fully glassy, and then a transient zone of partial crystallinity and probably complete crystallinity in the center if you had the full transition.
Ah, okay.
Which means, of course, that you could be suspicious about many people claiming to have made stuff fully glassy because they may not have looked much beyond the surface.
Okay. And is it able to crystallize towards the center because the composition then changes, or
so by and large in these systems, if you were doing this with conventional metal casting of alloys, for sure you would have segregation of elemental components. In these systems, by and large, you don't, except on a very local scale. So I don't expect any difference in composition across the cylinder. How it would crystallize is quite dramatically different from glass to glass. So at one extreme, they only show nanocrystals. At the other extreme, they show millimeter scale crystals that are perfectly evident to the naked eye. So you get a vast spectrum of behavior depending on the relative rates of crystal nucleation and growth.
I see. Okay, thanks.
Yeah, so maybe an additional question. I'm interested in the melting that you showed in the last part, Lindsay. So I find it very interesting because the molecular experiments from Mark Heidegger and others are really interesting. So I have a question about the glasses that you prepare with your process, and how do they compare with vapor deposited metallic glasses? So I read recently that's possible. Which one would be more or less stable in this respect?
Yeah, so thank you for raising the point about vapor deposited glasses, metallic glasses, because people in the metallic glass community for some time have been interested in looking for ultrastable glasses by the Wisconsin-Madison route, if I could put it that way. And they have published some very strange papers, including ones that are quite sure they're claiming ultrastable metallic glasses, but those ultrastable metallic glasses have higher energy than the normal form, which is the wrong way around. I have a rather extreme view on that little area of work of thin film metallic glasses, which, by people looking for ultra-stable states, is that it is entirely misguided. They, in order to get to lower energies, they use lower and lower deposition rates. And they have not paid sufficient attention to the fact that, of course, your sputtering is never perfectly clean, and you get an outgassing of species from the chamber walls. I am, of course, thinking principally of oxygen. At high deposition rates, that's not that important, but at low deposition rates, it means what you're actually depositing is a metal oxide. Now, I put that in extreme terms, but you might have a few % of oxygen in your deposit. For sure, that's plenty enough to affect the properties, possibly in a favorable direction, but it's not the metallic glass you thought you were looking at, is my point. There is, of course, a lot of work on thin film metals and thin film metallic glasses, and they can be quite well behaved and show very well studied diffusion behavior in multi-layered geometries, for example. So you can get perfectly good, dense, relaxed material, but I don't think it's a straightforward route to get ultra relaxed material.
So then the answer would be that the way you prepare glasses makes them more stable than the ones prepared via vapor deposition?
Certainly in the metallic glass case, I would say yes. Okay. Where by more stable, I mean with a lower enthalpy. And in a way, nothing else, without any assumptions about what the structure might be or whatever.
And just to be sure I got the curves correctly. So in the Madison, Wisconsin case, they see a shift of the temperature at which the glass melts, and in your case, you don't see a shift.
No, they don't. This is not melting, of course. Strictly, I mean, I would regard melting as crystal to liquid.
Okay.
This is glass to liquid.
Exactly, melting of the glass.
Yeah. Okay. So so yes, they do indeed see this. So what they're effectively saying is that you heat the glass, it wants to become a liquid. You will detect that happening when the specific heat takes off. And that is very much delayed in these super stable systems. Mm. So it fits in with that idea. I'm not sure Mark Edigo would agree with what I'm about to say, but it is in some way consistent with the idea that these glasses genuinely have difficulty going through the transition into the liquid state.
Yes.
And that it then propagates in from the surface or something like that.
Yeah, at least I don't know about Mark, but I do. And in your case, you don't see this shift, but you see a broadening, right?
We just see that this peak is broader than it would be for when you do it thermally, the peak let's say, a longer and longer anneal. The peak gets higher and higher, but it does not get broader. It stays the same width.
Yes.
Whereas with the mechanical process, it gets broader. But of course, that could just mean we have a rather imperfect process, which is giving us a very inhomogeneous sample. I don't know.
Okay, maybe we can discuss another time, but thank you.
Okay. Anything else quick, or should we wrap up? Okay. I guess so. So thanks again for a great talk and for entertaining so many questions. And yeah, we'll see you all again in a couple of weeks. Bye.
Thank you very much.